Okay, so in today's lecture, we will be talking about uniform and non-uniform motion. We're still within the one-dimensional motion. Today, we're going to be looking at the graphical representation and the interpretation for those graphs. The material that's covered today is from textbook section 2.2 and 2.3. So let me start first with the uniform motion. We have said that a uniform motion basically means constant velocity. And we've mentioned before that velocity has direction and magnitude. So when I say constant velocity, I means that the direction is fixed and the magnitude of the velocity, which is the speed here in this case, would be constant. So if I have a constant speed and in a straight line, for example, I have a constant velocity. So let's look at this one-dimensional problem that we have here. So in this example, we you are paddling a canoe moving north straight across a lake of a constant speed of 2 meters per second. The lake is 1,500 meters across. We need to draw the graph of the displacement of the canoe as a function of time. Let's set displacement equals 0 and time equals 0 second at the starting point, and the north direction would be our positive direction. So if I go here and I say this is my starting side of the lake, and this is the end of the lake, the distance between here and there is 1,500 meters. My north direction here is my positive direction. And I have the canoe here, the canoe is in the canoe paddling this way. So let me call this one V1. So in this case, if I am to write the equation that defines this motion, this uniform motion, for a velocity that's going in the same direction as my north, as 2 meters per second, then the equation that describes this linear motion is d equals, which basically d is the displacement, velocity, time, plus the initial displacement. So if I have here my 0 meter as my reference, and I'm starting from my reference point, which means I'm starting from 0, which means I don't have an initial. In this case, my d naught here is 0 because I am my starting point here at t equals 0 as 0. So we're going to go back to the question again and read the question for you who missed that. What we have is the following. You're pedaling a canoe moving north straight across a lake at a constant speed of 2 meters per second. The lake is 1,500 meters across. We need to draw the graph of the displacement versus time. So the problem is we have this lake. This is the direction of the lake that we're going to paddle through. This is the direction of my reference. This is north, and I'm going north. So since I am going north, V1 for me would be written in this equation as a positive, right? So I have here d equals to, this v1 is 2 times t. So this is my function that describes this linear motion. So what's going to happen, the canoeist with this uniform is going to pedal all the way till he travels 1,500 meters. Since my motion is a uniform motion, I have the velocity here being constant. So it is written as 2 meters per second, positive. And I'm starting from my reference point, which is 0 meter. That's why the d naught is 0, right? So I have here plus 0. So if I am to draw this function that is a straight line, I'm reading a question here. If we are to be going south, the velocity would be negative. We will see that in the second part of the example. So I know my motion here is a uniform motion, which is a straight line, because the velocity is constant. The direction and the magnitude of the velocity is constant. So in this case, I only need 2 points to draw this line. I'm reading a question here. How do we know that to set the d naught to? Now, the question is telling me that I am starting here from 0 meter. My reference is 0. If the question did not mention that, then you can pick this reference to be 0. At the end, you need a reference. You need a reference. See, what is your initial displacement? What is your initial displacement for the problem that you're solving? Let's wait till we see the second part of the example, and we will see where d naught is not 0. We're going to come to this. If it's given to me, I'm starting from the 0 meter, right? I'm starting from the 0 meter, then my d naught here is 0. So if I am to draw this graph for this straight line, I need 2 points. I have the first point, which is the displacement is 0 at t equals 0, right? So we have here t equals 0. Then if you substitute d with 0 at t equals d with 0, you will get t equals to 0, right? So this is the first point. So if I put here d being 0, then t is 0. This is the first point I'm starting with. Then the second point is I'll take it at the end. I need to find how much time it's going to take the canoeist to reach the end of the lake. So if I put here d 1,500 equals to 2t, then the time it's going to take, assuming we're starting here from 0 as 1,500 divided by 2, 750 seconds. So the canoeist with this speed, this constant speed going north, is going to take him or her 750 seconds to reach the end of the lake. So going back to here, my first point where I started is here at d equals 0. My time was 0. I started counting from that reference point. And then when the canoeist reached the end of the lake, which is the 1,500, this is the 1,500, I found that the canoes took him 750 seconds. So this is the 700, and this is the 750. So this is 750 seconds. So if I draw this line, I will be intercepting right at this point. And now the motion is described by this line. Why? Because it is a uniform motion. Because it is a uniform motion. Constant velocity. Now, if you want to verify the equation, you can pick some numbers. Let's assume that I picked the 800. Gave me 400. Going back to here, if I substitute in this equation, d equals 2t. If I say now d is 800, then t is 800 divided by 2, and t is 400. Right? If I take d to be 400, equals to 2t, t is 400 divided by 2, t is 200 seconds. So this is the motion that I managed to calculate based on the given information that were given to me, knowing it was a uniform motion, given the direction, given the speed, I managed to calculate that and graph that motion. Any questions so far? Okay, so again, for the I have a question here about the material that I asked you to read, which is section 1.1, 1.2, and 1.4. Those were the units, basically, and the conversion of units, how to convert units. If you find that those are still difficult to you to review, and of course the significant figures as well, then we can look into that as well. We find a way to provide you with more examples, or we can do that probably in one of the office hours and post that to you. Does this answer your question? Uniform motion is always linear. That's correct, because the velocity is constant. If you go to the course outline, you will see that one of the Zoom links was set up at on Friday at 9:30. Okay. So we're gonna deal with that conversions and those significant figures later on. Let's continue with, so you want basically, well, we usually use the SI units. I think metric would be the way that we will be using. But it doesn't hurt if you to know the conversion between, for example, miles and kilometers, all those conversions. I'm not expecting you to memorize all those conversion units. No, I'm not expecting you to memorize. We can add whatever you would like to be added to the formula sheet at the end. The purpose of this course is to make you understand the concepts and how to apply those rules and concepts, not to memorize. So this is not the objective. You're welcome. Okay, so keep in mind, I'm not asking you to memorize things here. I'm asking you to know how to apply those equations and concepts and solve those problems based on the understanding of the concept behind. Okay, so let's move on now and let's contemplate on the meaning of that graph that we just drew. So what is the slope of the graph? Let's go back to here and see what is the slope of this graph. Is the slope constant? Yes. And what is the slope? The slope of this is the velocity, exactly. And you can see that the slope is the same in any point of this figure, which means the velocity is constant at every point here in this straight line. So this is extremely important to understand. If you have a displacement versus time, the slope at any point represents the velocity. So we said that the slope represents the velocity. The straight line here means that the slope is the same, which means that the velocity is constant. So this is extremely important also to know. The velocity is constant in a straight line. Now, let's assume that when you reach the end of the lake, you've seen a threat and you decided to pedal the way back. You doubled your pedaling speed and you were moving backward, not backward, pedaling, the way back, I would say south this time, with a speed of 4 meters per second. We need to continue plotting the displacement versus time. So what would we do? So in this case, I want to say that V2 is 4 meters per second south, right? You're going south. That's the beginning of the lake, and this is the end of the lake. This is your reference north, and this is your 0 meter. This is your reference position. And again, the is 1500 meter. And now you're here. And now you're here, you're going this way with V2. So how can we plot this graph? We need to derive first the equation. So we're going back to the same equation, that is D equals to VT plus D naught. And now let me distinguish this equation, give it prime, and this is now V2. Now V2 with my reference here, north, and this one going south, it's going to be minus 4T plus D naught prime. How much do you think the D naught prime? Can somebody tell me how much is the D naught prime? Which is the initial displacement. That's correct. This is correct. So the initial displacement here, because I am starting here. Now I will reset my time here because I'm using now a different function. So I will reset my time. I will start counting from here, right? I will start counting from here and the way back. But I need not to forget that I have already traveled for 750 seconds. I traveled my first trip took me 750 seconds to reach to the end of the lake, and now I'm paddling the way back. However, I will reset my time and start at t equals 0 here, but my position is still with reference to this position, so my D naught prime is 1500. Why? Because I'm standing here. So this is D naught prime equals to 1500. So substituting now, my new equation becomes D prime equals to minus 4T plus 1500. Again, in order for me to draw the graph for this uniform motion, I need one more point. I need one more point. I have this point. I need one more point. So if I go back to here and I substitute D prime with 0, what does D prime equals to 0 mean? Why the 4 is negative? Why the velocity is negative? Remember, what did we say about the velocity? We said the velocity is a vector. In the first part of the example, we had you paddling north. Paddling north means that the velocity is pointing in the same direction of my positive reference. That's why I wrote V1 as positive. But what is the scenario now for the paddling south? You're paddling south, you are in the opposite direction of your positive reference, which means things here have to be different than the first scenario. In the first scenario, you're traveling in the same direction of your positive reference. In the second scenario, you're paddling in the opposite direction of your positive reference. So the velocity has to be negative in this case. And that's why we substituted V2 with minus 4. Now, if I am to substitute D prime with 0, this means I am calculating. So this point is that D prime equals to 0. I am calculating the time you are taking to reach the starting point. So if I put d prime equals to 0 in my equation up there, I have 0 equals to minus 40 plus 1500. Now you're going to take the minus 40 to the other side. You're going to take the 1500 to the other side. It's up to you. But at the end, I have 40 equals to 1500. And then t equals to 375 seconds. So it took you to come back to your first point 375 seconds. So back to here, we said that we have reset the time. So this is the 750. If I add 375 to it, I will get my new point. Which is 1,125 seconds. I'm counting from the last point, from the last moment I've reached at the end of the lake, right? So from here to here, this is 375 seconds. Let me have a look at your questions here.
I just had a quick question about the last slide.
Sure.
What is the slope of the graph? I just missed that answer, and then the next question as well.
The slope of the graph is the velocity. If you look at the slope here, this is 2 meters per second. It's a positive because we were going in the same direction of the reference. If you look at the slope here, it's steeper than the first one. However, it is negative. It is -4. And in our case, since it's a velocity, it takes meters per second.
Okay.
So you're welcome. So you can see that for a straight line, the slope is constant, which means that the speed is also constant, or the velocity is also constant, because here this is positive, this is negative. Okay, so any questions so far about?
I have a question.
Yeah.
Can you just go over why the d prime is 0 in the second example, but in the first one, d prime is 1500?
Right. So my reference here is the starting this side of the lake. This is my position reference, which is 0 meters. Reaching the end is basically reaching a displacement of 1500. If I come all the way back to here, I would be at the position of 0. So that's why the d prime here is 0 and the d here was 1500.
Okay, that makes sense. Thank you. Does d prime represent displacement then?
Yes, the d prime also represents displacement. The same equation is applied. However, I called it D prime just to distinguish between the first equation for trip number 1 and the second equation for trip number 2. But at the end, D is the displacement, V velocity, T time, and D naught is the initial displacement.
Okay, thank you.
You're welcome. So back to here. Now the question is, why did we add the 375 to the 750? We added that because we have started from here, from this point where we took our time equals to 0. So the difference here now between, for this motion, the way back is a 375. If you add it to the 750, you get the total time the trip took, since we have two different functions. So in the canoeist example, in which the displacement is plotted against time, what does negative slope mean? I think we talked about that. And we have seen that the negative slope here means that the velocity is going in the opposite direction. Yes, that's correct. Opposite direction of our positive reference. Now let's move to the next example here. In this example, we have a person initially at point P here. This point P is at position 2 meter, right? So this is my reference position, 0 meter here. So a person initially at point P is, in the illustration, stays there a moment and then walks along the axis to Q at a constant speed. So he's walking to Q at a constant speed, right? Now remember, he stayed at P for a moment. I'll call this moment T, T1, for example. And then once he reaches Q, he remains in a Q for a moment. So here at the Q, he remains for a moment. Let me call it T2. And then he runs all the way to R with a constant velocity. And then he stops at R. Which of the displacement versus time graphs below best represents this motion? Okay, some of you are saying D. I have D, A. Okay, so let's do it together. What I'm going to do, I'm going to copy this. I'm going to go here. And paste it. Here. So again, time, displacement. Okay. Some of you got right. I'll tell you later on which one is the right one, but let's do that together. We'll see. Okay. Some of you got right. So this is position 0. This is position 1, 2, 3, 1, 2, and 3. So at the beginning, that person was at P, which is here, and he waited for a moment. This waiting, the time is running, so he's not moving, time is running. So you go this way. Displacement versus time. This is a delay. He was there at point P. He waited for a moment, which means he's not moving. That's why he was at 2, but the time was running. So this is what meant by he waited for a moment. And then what happened? She went to Q, walking with a velocity v1. Now, this is very important. Look at your position, at your positive direction. It is going to the right. She's going in the opposite direction, right? Which means her slope is negative. She's going to position number 1, walking, so her slope is negative and it's a straight line. So in this case, so this is P, point P. Now she reached point Q and she waited for a moment. Waiting for a moment is a delay. So she is right now at Q. Right? And then what? And then she ran to R with a velocity v2 that is constant. What does this mean? She is going in the same direction of the positive reference, so her slope is positive, right? She's now running, which means that her slope, the slope is steeper. So, and she is going 2 steps in position. So she's jumping now to 3, which is the location of R. So she's going to go like this. Notice that the slope is steeper because it is faster, and it's positive because it is in the same direction as the positive reference. Then she stops. Make sense? Okay, so let's move on. So the answer to this is B. So we have seen in uniform motion that a straight line basically represents a constant velocity, right? However, if you want to now draw the velocity versus time graph in constant velocity, what do you get? Let's try to do this here. Let's take those points. So this is velocity, right? No motion, 0. Negative slope, constant, right? Constant velocity. No motion, 0. Positive, no motion, 0. So this is the velocity versus time graph. Now, an example here is asking us to plot the velocity of the canoeist versus time and determine the displacement of the canoids for the first 750, between 750 and 1,125, and the total displacement of the canoids. So let's go back to here and redraw the displacement. This is for the displacement versus time. Let's draw the velocity versus time. At the beginning here, we had a positive. We have a positive slope. Remember how much was the slope? 2. And then the negative minus 4. So this one is minus 4, and this one is 2. So if you calculate the area below the velocity, what do you think you get? So let's do the area 1. Two times 750. What do you get? You get displacement, right? If you calculate area 2, which is minus 4 times 1,125 minus 75, what do you get? Minus 1,500, right? And that's the displacement. But guess how much the total displacement would be? Zero. And this makes sense. Why? Because we have seen earlier that if we come back to the same position, the displacement would be 0. Remember from last lecture, when we said that in displacement, if you come back to the same point, the displacement, which is a vector pointing from the starting, ending at the destination, if the destination overlaps the starting point, then the displacement is 0. And this is what we have seen here. Displacement is 0. So now let's move to the non-uniform motion. In non-uniform motion, the velocity is not constant. Saying the velocity is not constant, meaning that either the magnitude is changing and the direction is fixed, or the magnitude is fixed and the direction is changing, or both. One of the special cases, you have the direction, for example, here, when the direction is fixed, you have a straight line motion. However, the velocity is varying along this straight line motion, right? So this is the case that you have a straight line, non-uniform motion. Direction is fixed. However, the speed is changing. If you recall from last lecture, we did calculate the average velocity over a period of time. Now, if I'm interested to calculate the average velocity on a specific period along the path itself, this could be the following here. If I have a cat, for example, that jumped running after a mouse, you can imagine that her velocity is going to start from 0 when she was at rest, and then her velocity is going to increase. Why? If you look at the slope at every single point here, you would see that the slope is increasing. And this indeed defines the velocity. And that's why we say in this motion that the velocity is non-uniform. Is it changing? Right? The velocity is it changing? Now, if I want to calculate the average velocity for that cat between 2 seconds and 4 seconds, what do I do? I come to the 2 seconds and I intercept it with the function. I come to the 4 seconds and I intercept it also with the function. Then I project it on the displacement, take the reading, project it on the displacement, take the reading. I know the difference here in time. Delta t is 2. I can calculate delta x, which is 6. Then the average velocity is delta x divided by delta t. So in average velocity, the 2 points that I am taking their displacement are part of the function. Now let's assume I want to calculate the average, not the average, the instantaneous velocity. What do I do? In the instantaneous velocity, at, for example, 4 seconds, I want to calculate the instantaneous velocity at 4 seconds. I come to the point 4 and I draw that tangent. And I take any 2 points of this tangent to calculate the slope. Right? So if I am interested to find the instantaneous velocity, I draw the tangent at this point of interest and I calculate the slope for this tangent. This would be the velocity, the instantaneous velocity right at this point. So in summary, in average velocity, the 2 points belong to the curve that I am reading the displacement for. In instantaneous velocity, the 2 points belong to the tangent. Any 2 points from the tangent will give me the slope of the tangent line. And this would be the velocity at that point that I have the tangent line on. Finally, let's look at this example and try to understand how those 2 trains are moving in this graph. So the graph shows displacement as a function of time. So we have displacement as a function of time for 2 trains running on parallel tracks. I'll ask you, and you tell me, which of the following is it true? See, this train A is going in a straight line, displacement versus time. Train B is nonlinear, as you can see. However, they are intercepting here in displacement at this moment. So I will ask you, and you tell me if it's true or not. At time TB, do you believe both the trains have the same velocity from your understanding? Okay. That's a bit tricky. Okay, I'm getting now mixed answers between true and not true. Okay, so what we have seen earlier, that they share the same displacement. But look at the slope. Exactly, you got that right. Look at the slope. Is the slope the same for both of them? No, it's not the same at that point. This means the velocity is different. So they don't have the same velocity. B, both the trains speed up all the time. Do you believe that both the trains are speeding up all the time? No, you got that right. Why? Because we can see here that train A kept a constant velocity. However, train B went into changes. Train B started with a higher velocity, and then he started to decrease this velocity till he becomes the same, and then the velocity starts to decrease back again. So B is wrong. Both the trains have the same velocity at some time before TB. Do you agree? You don't agree? Yes. Yes, they do. I'll show you how. Look at this point, for example. This point right here. If you draw the tangent line, don't you think that the velocity is the same as the velocity for train A? Excluding the zero. Let's look at the zero as a singular point. Here, right here. Don't you think that the slopes are the same right at those points? Slope for A, it has a constant slope. Well, we understand that. But what do you think of train B right at this point? Doesn't have the same slope? Right at that point, yes, they do, because they are parallel. Thank you so much. This ends our lecture for today.